All right, so in this one, we'll practice this here. This is case 7. An ideal gas is in a sealed container with movable top. Person changes the volume from 0.0187 meters cubed to 0.00973 meters cubed. If the original temperature was 16 degrees Celsius, what is the final temperature in Kelvin? And the pressures kept same throughout the change. So what I want you to do is go ahead and set this up, gas before, gas after. All right, we'll get this into Kelvin here. So the gas before, gas after. See if you can solve for the final temperature in Kelvin. And so once you do that, you can hit play to continue. So go ahead and pause, and then we'll take a look at it. All right, so pressure is the same from both sides, so we can divide both sides by pressure, divide both sides by the number of moles of gas, so that's not changing, and then the gas constant is not changing, so we end up with a ratio of volumes and temperatures, and we should get a temperature of 150.37 Kelvin, so that should be the final temperature. In Kelvin, the initial temperature was 289, okay? And so to keep the same amount of pressure, as this compresses here, the temperature's got to drop to keep the same amount of pressure. Okay, and then in this situation, what would happen if the volume was fixed and temperature and pressure were allowed to change? And so, temperature and pressure allowed to change, but the volume is fixed. So try this in the simulation in PhET under gas properties, and give this a try. See what that looks like if you keep the volume fixed, but then you increase the temperature. What would happen to pressure? All right, so what you can consider with this is, for instance, let's say you had a container like this, a metal container that's a fixed volume, right? And the volume's not changing. So if you keep heating this up and the gases are moving faster and faster and faster inside here, right? Eventually, right, it can be, you can get very, very high pressure, and then if something's wrong where the pressure gets so much, you can have an explosion where one of these valves, if the pressure builds up too much, maybe it'll explode. And so, as you're dealing with higher and higher and higher pressures, it takes more and more and more, integrity of the structure to be able to withstand that. So I show in this clip, an oil tank explosion where the pressure built up so much that eventually the structure gave way and explodes. So this is the Gay-Lussac's law, where the volume is constant, pressure is directly proportional to temperature, and the pressure is in pascals, temperature. So again, with dealing with the ideal gas law, we can combine all these different relationships into one, where the pressure and volume is directly proportional to temperature. So pressure times volume is directly proportional to the temperature. And then in terms of the amount of gas present, the temperature, pressure, and constant volume is proportional to the amount of the gas. Then, we have the relationship with the mass as well here. So if we're not introducing more mass into the system or taking away mass, we can consider that there. So, all right, so as we talk about quantity of gas, what's going on with gas, the mole is a really helpful thing that we use. And so go ahead and draw a box representing a gas inside this box. And inside this box, if this is 1 mole, you have many, 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 and it's actually a fixed number of molecules. And that value is 6.02 times 10 to the 23rd. That's a lot of them inside, okay? Now, let's do an example. Let's say that we have helium. And let's say that helium 2, okay? So they're together. Now, what does that actually mean? You have a helium nucleus, so plus, neutron, neutron, plus, proton, proton, neutron, neutron, okay? You have the electrons. Actually, 1, 2, 3, 4, 5, 6, 7, 8. Now, what makes a molecule? A molecule is where you have 2 nuclei sharing electrons. So let's say that this right here represents helium-2, right? And that is one of these black dots. So there are 6.02 times 10 to the 23rd of them. There are many, many, many of these, okay? Now, that is a mole. We have 1 mole of them. And, yeah, of helium. In terms of using number of moles, this could be a really, really helpful thing for us. And so 1 mole of an ideal gas has the same volume. And so, 1 mole occupies the same space. The number of moles, number of molecules in 1 mole is the same as well, and that's really helpful for us. And so when we talk about what's going on with atomic theory, that's important to consider with this too. The atomic and molecular masses are measured in the unified mass unit. So 1 U is 1.6605 times 10 to the negative 27 kilograms. And so let's figure out the mass in kilograms of 1 H2O molecule. And we can do that here. So we want to find the atomic mass, and we convert that to kilograms. And so we have our values here, we have oxygen here, we have our hydrogen here, and we have our, water molecule here, one oxygen, 2 hydrogen. And yeah, so if you can see if you can do that. What's the mass in kilograms of 1 molecule of water? So go ahead and pause the clip and try that. And when you're ready to check, you can hit play to continue. All right, so the atomic mass, you have 2 hydrogens, you have 1 oxygen, so the amount in U is 18.01528 U. 2 oxygen or 2 hydrogens, 1 oxygen, and we convert to kilograms, and we should get 2.9914 times 10 to the negative 26. What you basically do is you set up your bracket here. You've got U, so 1 U is 1.6605 times 10 to the negative 27th kilograms. So in 2011, we had the earthquake in Japan that was very devastating, and they had the explosion at the Japanese reactor. And I'm not sure if this link still works, but you can Google search that and read about the nuclear reactor. And so essentially, what happened there directly relates to what we're talking about with the ideal gas law here, where you have pressure building up so much, and it's contained, and then when it can't be contained anymore, it's open to the open, and so that those radioactive particles are released into the atmosphere and get on substances, and it can be pretty yucky. And so it's important to consider the the gas laws for a lot of different things, including safety with nuclear reactors. So this is K9. What we want to find out is what is the mass in kilograms of an O2 molecule. So this will be good practice here. Go ahead and pause the clip, give this a try, and then when you're ready to check, you can hit play to continue. Okay, so we've got H2, or O2 rather, 2 oxygen molecules, so 32U. We convert to kilograms, so 5.314 times 10 to the negative 26 kilograms for that. Okay, now the mole. The mole is defined as the number of grams of a substance that is numerically equal to the molecular mass of the substance. So, in other words, if we had 1 mole of H2, right, 1 mole, so here's a container, and in this container we have a lot of these molecules, right, a very specific amount, we'll talk about that. And then H2 has a mass of 2.02 grams. So that is how much, if we had a gas, right, this gas, and we put it on a scale, and we would read that, we would have 2.02 grams is how much that would be. And the way we got that, if we know what hydrogen is, this is 1.0079 U, right? We have 2 of those. We have the corresponding grams. And so in other words, like with this, we have this is U for neon, right? That's the atomic mass. So therefore, if we have a mole of that, right? And so actually kept at the same size as this, right? So same size, and we have all of those neon molecules inside, right? 1 mole of that, 1 mole of neon, is this many grams. And so if we put it on a scale, we would read 20.1797 grams because of all those different molecules in there. If we have CO2, it's 1 carbon, oxygen, 2 oxygen atoms, right? So we add those up in U, and so that container would have, we measured it, would have 44 grams of mass. And that should make sense because every mole has the same number of molecules, the same number of dots. There's the same number of dots in here, same number of dots in here, same number of dots in here. Each dot represents 1 molecule. And so therefore, if you have the same number of molecules, each molecule has a different amount of mass. And so therefore, if you have the same number of CO2s as you have H2s, right, you're obviously going to have more mass. And so that's what we're dealing with there. So the number of moles in a certain mass is, or the number of moles in a certain mass of material is this relationship here. And so hopefully that makes sense there. So mole is defined as the number of atoms in 12 grams of 12 carbon. So 1 atom of this is 12 grams. All right, so let's now go ahead and apply this for fluorine gas, F2. So yeah, go ahead and give this a try, and when you're ready to check, you can hit play to continue. Okay, so fluorine is 18.8 or 18.998. So if you have 1 fluorine atom, that is 18.99, but we have 2 of them, right? So we have, the 2 nucleus, a bunch of protons, neutrons, bunch of protons and neutrons. They're sharing their electrons. And so we have 2 of them. So we have 18.99 times 2. And we get 37.996 U for 1 molecule of fluorine gas, right? Now, according to our definition with a mole, 1 mole then would weigh 37.8 or 37.996 grams. So if we, actually took that box and weighed that box, that's how many grams we would get. Therefore, if we have 3 moles of that, that's times 3, that is going to be 113.988 grams. And that's how many grams 3 moles will be. Now, let's go ahead and add this one here. What is the mass of 4 moles of nitrogen gas? So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so we have, nitrogen, N2, which would be 14 times 2. And so that's 28 U. So 1 mole of that would be 28 grams. We have 4 moles of that. So we have 112 grams of nitrogen gas.